So welcome everyone. Today our agenda is to take a deep dive into OFDMA. Our chief scientist, Steve Shear, has some really good material to explain how and why OFDMA works and when it's best to use. Steve has over 20 years of experience in Wi-Fi directly, most recently with the Wi-Fi Alliance, but prior to that with other wireless technologies, including GSM, TDMA, CDMA, and he's been involved in several standards, important standards efforts, in addition to the Wi-Fi Alliance certification. And Prachi Samkuar is our systems engineer. Both Steve and Prachi are based in the Bay Area in California, where they work with customers directly and with the octoBox system, configuring and running tests. And Prachi has experience with Intel prior to octoScope. So with that, I'm going to let Steve take things over. And the rules of engagement today are, we are obviously making the effort to come to you live. We're doing this tutorial 3 times a day to reach all the time zones. And so we do welcome direct questions. Feel free to post your questions in the Q&A or raise your hand so you can ask them live. We're going to try to stop at the end of each slide or every couple of slides. So give us a little time and we'll get to your question. And with that, we're ready to go.
Thank you, Fanny. Thank you, everyone, for joining to listen in. Just as an introduction, I want to point out that Wi-Fi 6 testing is really a departure from previous generations of Wi-Fi. In the beginning, we had 802.11b that evolved through A and G, later through 11n, which was known as high throughput, Wi-Fi 4. 11ac came in as very high throughput, or Wi-Fi 5. And even the new 802.11be is known as extremely high throughput. So all these previous generations have been focused on giving higher and higher throughput to individual users. 11ax is different in a sense, insofar as it focuses on high efficiency for a network, not just increases in throughput. This is important for dense environments like airports and sports stadiums and these kinds of things. So when we think about testing Wi-Fi 6, we should make sure to exercise those parameters. Today we're going to focus on 2 key Wi-Fi features: MU-MIMO and OFDMA, and these are important aspects that improve efficiency of the spectrum, especially, as I mentioned, in dense environments. Before we go on, I'll just touch on the new MCS values that Wi-Fi 6 brings in. Wi-Fi 5 was 256 QAM. Wi-Fi 6 brings in 1024 QAM, so that's quite a dense constellation. It allows you to convey basically more bits per second, and that together with the 160 megahertz bandwidth really more than doubles the available throughput. So this is also a significant benefit of 11ax. So these efficiencies that we talked about are gained really in two key ways. MU-MIMO increases the capacity by creating simultaneous full capacity physical layers, and it does that through beamforming, as you can see in the diagram on the side. It currently only operates in downlink direction, but Wi-Fi 6 R2 will have that working in uplink. OFDMA increases efficiency by allowing up to 37 users to be on the air simultaneously. And this has a huge benefit in reducing overhead for each frame. We'll take a look at that in a little bit more detail later on. OFDMA works in both the downlink and the uplink directions. So it's pretty much fully fledged in R1. We'll take a little step back in history. We've always had frequency division, multiple access. This is a conventional frequency scheme. It allows different users to have different services, and they do that by allocating different channels. Orthogonal frequency division, multiple access, is much more efficient than the traditional FDMA because these subcarriers are orthogonal and they don't require guard bands, which is a waste of spectrum. The other interesting thing about this is that, unlike FDMA, these individual carriers can be allocated dynamically. So one can allocate a number of carriers to a particular device depending on its data rate requirements and so on. So this is done on a dynamic basis and results in a very efficient system. An important aspect, though, about OFDM is that these carriers must be orthogonal. So by orthogonal, what we mean is that adjacent carriers do not interfere with one another. And if you take a look at the response there, you'll see it goes through 0 right exactly where each adjacent carrier is. This allows us to optimally space these carriers and make use of the frequency domain a bit more effectively. So on the right is a diagram just pulling out that particular aspect. In OFDMA, we have multiple independent stations that are transmitting simultaneously, and they need to make sure that they've got phase lock, so that their tones are orthogonal with tones from other devices participating in the OFDMA exchange. If that is not an accurate phase lock, these tones can move across like this, and you can see they generate interference in the adjacent tone. So very important aspect of maintaining accurate phase lock and frequency as well. Basic principles of OFDMA. Each user is given an association identifier. There's the usual preamble, which we see as a standard part of Wi-Fi. It uses the full bandwidth of the channel. The difference is that the payload for each user or each AID is sent in different portions of the spectrum. And these portions of spectrum are called resource units. So the allocation of AIDs to resource units or resource units to AIDs is done on a packet by packet basis. It's very dynamic, and it makes studying the OFDMA performance quite interesting. A key part of OFDMA is the trigger frame. The trigger frame is sent by the AP. It contains information about which participating devices are going to participate in that particular frame. And it provides a time, a frequency, and a power reference for the devices, in this case, that would be doing uplink OFDMA. There are very stringent requirements on the timing of devices to respond. Ideally, they should all respond simultaneously. So there is a tolerance allowance of plus or minus 400 nanoseconds that they have to meet. And this is actually tested by Wi-Fi Alliance in their certification program. They also have to maintain very accurate carrier frequency offset, plus or minus 370 hertz, which is very stringent indeed. And together with that, they need to control their transmit power to facilitate proper AGC operation at the AP receiver. So quite a lot of detail, performance-related stuff that OFDMA brings into the mix. I'm going to look at some of the efficiency gains that we talked about for OFDMA. The top diagram depicts what happens when we're sending, for instance, small voice packets that just are not able to fill the complete 160 megahertz channel capacity. There's a lot of overhead leading up to the actual useful information, contention period, RTS and CTS and preambles and stuff. And if you just take a look at the ratio of the amount of useful information to overhead, again, especially for short packets, you can see this is legacy Wi-Fi is can be quite inefficient. OFDMA essentially squeezes each user's data in frequency, and it stretches it out in time. What that means is that the whole protocol exchange becomes much more efficient because the ratio of the actual useful data to the rest of the overhead is minimized as well. But another important aspect here is that in the upper in the legacy system, you have to do a channel contention for every single packet that you send. With OFDMA, we're packing, in this case, 9 users into this packet, and we only have to do one channel contention in order to get the data to those 9 users. So just intuitively, you can see there's a great gain in efficiency there. I didn't draw a diagram for 37 users, but one can. The standard allows packing 37 different users simultaneously into the 80 megahertz band, and indeed 72 in 160 megahertz bandwidth. So this is a depiction. These are drawn roughly to scale, and gives one an idea of the benefit in efficiency there. So let's think a little bit about testing considerations. We've spoken about the need for many devices. That's what Wi-Fi 6 is designed for. We should really be testing these new features in the way that they were designed. So we have a thing we call the palBox. This contains 16 individual stay pals. These are physically individual stay pals. They will run on a Pico ATX board. We make use of the Intel AX200 receiver, and we have different flavors of Linux and Windows. We also group them in 4 groups of 4. These are 2x2 stations, and we feed the signals into the corners of the testing chamber. This gives us the maximum spatial diversity for each of these groups. It means we can test MU-MIMO in this chamber, and that works very effectively. But again, with the number of stations here, we can very effectively test OFDMA as well. These are some of our PALs. PALs are test instruments. The stay PAL is the little guy up on the top right there with the 2 antennas. As I mentioned, it is a standalone station with its own computing power inside it. We pack 16 of these into a palBox. Makes for a great deal of parallel processing in that box. And it also contains a PAL6 as well. You can see the stack here with the palBox door open, cram packed with these. So we talked about the antennas coming into the corners of the chamber. This is an important aspect to get spatial diversity, and this is a kind of close-up of these antennas. We use these high-gain antennas because we found them very effective for doing MU-MIMO. It's an excellent way to couple to the device under test with as little loss as possible. And for devices that don't have antenna connectors and so on, this is a very practical way of doing things. Let's take a quick look at MU-MIMO. MU-MIMO, single user MIMO can really only service one user at a time. This is kind of the legacy Wi-Fi that we understand, where one device is serviced at a time, essentially time sharing the channel, and that limits the amount of traffic that you can get to each device. In the case of MU-MIMO, it effectively creates individual PHYs by using beamforming, and this can simultaneously serve each of these spatially separated users. So this gives us actually a much higher aggregate throughput for the network. And just as an example, if we had 3 MU-MIMO users, we'll get nearly 3 times the aggregated throughput. So a very effective feature of Wi-Fi 6. I'm going to run a demo of MU-MIMO, Wi-Fi 6 MU-MIMO. I'm going to select 2 PALs from opposite corners of the box, and we're going to run MU-MIMO traffic. We'll start off with in single user mode, and then we will switch that on. Let me just pull this up here. So we have a number of traffic pairs on the left-hand side. I'm going to start the experiment running. So here we see the throughput for each user, the red and the green user. They're getting approximately the same throughput. The aggregate throughput's up around about 900 or so, and this is typical for single user MIMO. We're running at MCS 10 at this point, and our data rate is a little over 1,000 megabits per second. So I'm going to go ahead now and switch MU-MIMO on. We can do that in this configuration screen. So here I'm switching this guy on. I'm going to send that configuration down to the PAL6, which will go offline as it reconfigures itself. You can see the data has stopped there, and I can monitor the status of the PAL6 with this little hover over window. So this will take a few more seconds before it comes back on. There we go, that started to come online. We can see the stays associating. We'll give it a little bit of time just to stabilize. This is a fairly disruptive event, okay? So stays are still associating, and I'm waiting for the green guy to associate. So you can see the red one is making use of the full use of the channel. Here comes the green guy. So now we see that both the red and the green guy are getting higher throughput than they did before, and the overall aggregate throughput is higher as well. I'm going to leave it just to run for a few more seconds. There are some training sequences and so on that are going on to try to optimize this. So this is so this is a good
so you
demonstration.
can see MU-MIMO gains with 2 stations. There may be decreasing gains with more stations, but with 2 you will get optimum gains. There was a question why we have Linux and Windows stay pals. And the reason is our customers want to see both, because drivers are different, OSs are different, TCP, UDP stacks don't perform the same way. In fact, we see a lot of differences in performance. So we have mixed them up. There's another question. Can you observe similar MU-MIMO total throughput with 4x4 router or 8x8? Is 8x8 required for spatial diversity? So that's a good question. Theoretically, you can form a better beam with 8 antennas versus 4. In practice, we have not seen good performance with the 8x8 devices that are available. And we are using 4x4 here. But it's a good question, because ideally, you've got more antennas to form a better beam, right? But we're using 4x4 here and 2 2x2 stations.
Okay, thank you, Fanny. So we're going to move on, and I'm going to show you an OFDMA demo. So here we're running with 8 stations in the palBox. We've disabled MU-MIMO operation. Again, we're running 2 stream stay pals on a Linux OS. And we're going to be looking at ping latency. So here you see the 8 traffic pairs. We have a large number of devices associated. I'm going to get this running. It'll take a little time to load. Okay, here we go. So we're looking at the graph of ping latency down in the bottom here. This is with OFDMA off, and you can see there's a fair amount of latency. There is a big spike there, but most of the latency is around 100 milliseconds or in that order. At this point, I'm going to reconfigure our PAL6, and I'm going to switch OFDMA on. Just like before, we're going to send the configuration down. The PAL6 has gone offline, and the data traffic has stopped. So we'll give it a few seconds for it to reconfigure itself. So this is coming back up again now. The stays are all associating. Still a few to go, I think. And the data has started running. So now I want to draw your attention to the latency in the graph down below, and notice how considerably reduced it is. So I'm going to switch off this graph here, which will allow us to rescale the graph. So here on the left-hand side is a ping latency with OFDMA off, and on the right-hand side is ping latency for all of those 8 stays, but this time with OFDMA on. A couple of spikes. I think these are due to the the transition and stuff queuing up and so on. But these are all very, very closely grouped together. And if you zoomed in there, it would be below the 10 millisecond range, whereas previously we were looking, 60 to 100. Now I'm going to hand over to my colleague Prachi, who is going to show us a Wi-Fi 6 throughput demo.
So this one is a classic rate versus range test, which I'm going to show you. So I'm just going to dive into it directly. All right. Okay. So here, what I'm doing is I'm running my traffic from the AP to one of the stay pals. So you can see with Wi-Fi 6, you're achieving theoretical performance. We are getting a throughput of around 2 gig. And one of the benefits of using our stay pals is we can see a number of underlying metrics. So on the graph here, you can see that we are able to see at the RSSI, that is the data RSSI per chain. We are getting a data rate of around 2400. We are running an MCS of 11. Again, as I mentioned, the stay pal is a 2-stream device, and we are operating at 160 megahertz. So, and this one is we are running at an adapting MCS. If you guys want, we can run it as a fixed MCS too. And on the left here, you can see that we are simulating range by using attenuators. And as soon as the attenuators increases, you can see a drop in the RSSI here on the graph, and a corresponding drop on the throughput also. So this is this shows us the performance of Wi-Fi 6. And if you guys have any questions, please feel free to ask.
All right, nice test. Thank you, Prachi.
Yep.
So we have a question. Is there any difference in the stay in blue color versus red? I think you may be referring to that diagram. The blue was Windows and red was Linux. So we do have a mix of Windows and Linux stay pal.
Oh, okay. Stay pal, okay. Yes, Steve, you can go ahead.
Okay, thank you. Let me try to get this up and running again. Okay, so as you saw from Prachi's demo, there's an enormous amount of data that we collect. I mentioned that we store this in a Mongo database. We can extract it and look at it later. We can post-process it. A lot of interesting information is captured in there. But I'd like you to give some thought about what all that information looks like when we have 37 simultaneous devices. Even the analysis of that information in a Wireshark screen becomes very, very complicated. There's a tremendous amount of data. And to try and get some sense of how your OFDMA system is performing is very tiresome to look at the detail in Wireshark. I mean, that is a necessary thing to do, especially for debugging. But sometimes it's useful to get a kind of a big picture idea of how the device is performing. So let's just remind ourselves the diagram on the left is the legacy Wi-Fi spectrum. Single user at one user at a time. The diagram on the right depicts an OFDMA where we have multiple users in the same packet, and it very quickly becomes apparent that we need new methods to visualize its performance. Otherwise, it's very difficult to get the big picture. So we've actually represented this information in a 3D plot here. This is actually a plot using a commercial AP. There are 24 state pals participating. We've actually got 7 cell phones in there as well, and that's a total of 31 unique AIDs. We differentiate the AIDs by color. We can look along the time axis. We can see the RUs that are allocated in the frequency axis. And since, just to add further complication, each AID can be assigned a different MCS. So we take a look at the MCS for each one of these allocations in the Z-axis. So this is one picture here. You can see a mixture of wide and narrow RUs. See a mixture of higher and lower MCSs. This is another one, same AP. We're actually running in 20 megahertz bandwidth. These are actually very small packets to simulate voice, and you can see the distinct sort of difference in characteristic of these two graphs. This one is doing voice. This guy is just basically doing like a throughput test. In the voice packets, nearly all of these are narrow RUs, and it's very useful to have this sort of helicopter view of that. Now, to extract information in OFDMA, you need to assign a sniffer per AID, and this is where the palBox really springs into its own, because you can assign one of these state pals as a sniffer to monitor its own, or to monitor a particular endpoint. So we can set up a number of OFDMA sniffers and a number of endpoints, and we can get a very good picture of what's happening in this OFDMA system. Of course, these sniffer probes, we call them, need to be synchronized. And so we use the term synchroSniffer probes for OFDMA. So next time we'll dive into this very interesting topic, the topic of synchro-sniffing for OFDMA and roaming as well. In fact, there are a number of other scenarios where synchro-sniffing is important. Of course, this requires all of our probes to be synchronized, and we have a method for doing that. We'll be discussing that in more detail in the next tutorial session. So I think we have a few minutes left over, and I'd be very happy to try and answer any questions if you have them.
Yeah, there's one question. Can I test TWT and BSS coloring using staples? And the answer is yes, we can. We may be showing some tutorial on that down the road. So as far as TWT, we ourselves have not tested it. We've tried. Intel AX200 driver appears to be broken in some ways, and so we're still not getting TWT with any stations that we have. But we do have the capability, and it's enabled in our PAL6. So staples waiting for it to be fixed. That's the answer. But the testbed does support these tests, and we plan to do them both. The coloring is a different test, so that's also coming. And the testbed as is will support it. We have a specific signal flow of the traffic for it with the adjacent overlapping BSSs for coloring.
Thank you. Good question. And any other questions? So I am based in the Bay Area. Hopefully things are going to get back to normal, and you'd be welcome to come and visit our facility there. But in the meantime, if you have a particular topic that you'd like us to cover, something of interest to you, please feel free to drop me an email directly, and we'll see what we can put together to cover that for you.
There's another question, Steve, you may be able to answer. How is the participation in the uplink OFDMA frame negotiated? Is there an exchange required?
Oh yes, right. That's a good question, and it's a very important aspect of OFDMA. So I'll take you back to this diagram here. It's not really a negotiation as such, although one could think of it a little bit in those terms. The trigger frame that the AP sends down contains in it information about who the access point, which stays the access point wants to hear from. So that's where it basically lays it out. And if you take a look at a trigger frame, you will find the individual AIDs actually listed in that. So that's the dare I say, trigger that controls the transaction.
Okay, there's another related question, so stay there. Is uplink OFDMA, in uplink OFDMA, does each stay send its own preamble? So the answer is yes, but there is also a common legacy preamble, which is on a previous slide, I think. But you can see on this slide, once the OFDMA is all negotiated, then each state sends its own OFDMA preamble. But prior to that, you have a legacy preamble which participates in all the CSMA-CA stuff. So I think you have that on the previous slide, Steve. Yes. So see that preamble, that's a legacy preamble. But once you have stations jump in on their RUs, they also have OFDMA preamble. All right, folks. Well, thank you very much. We're delighted that you joined us, and we look forward to hearing from you. If you have any further questions or would like to come and play with the gear.
Yeah, thank you. Thank you very much for listening.
Okay, bye-bye, everybody.